In this video, we'll discuss how to improve bandwidth using a dipole antenna. This type of antenna is well suited for enhancing your Wi-Fi signal performance. When transmitting data, we use a carrier frequency to carry the information. In this case, we're using 2.4 GHz, a widely utilized frequency band primarily used for Wi-Fi communication. The transmitter generates a 2.4 GHz RF signal, which is fed through the transmission line, typically a coaxial cable. When the signal reaches the antenna's feed point, it induces an alternating current in the antenna's elements. This alternating current produces a time-varying electromagnetic field around the elements, which radiates outward as an electromagnetic wave. Now the transmitter sends out our 2.4 GHz from the transmitter through this coaxial cable to the antenna. This frequency is known as a resonant frequency. Now 100% of this frequency is radiated across the airways. Once the length of these two elements are equal to half the wavelength. And I'll explain exactly what that means right now. This symbol here stands for wavelength, which is equal to C over F. C stands for the speed of light and F stands for frequency. Now here we have it right under here. C, speed of light, which is 300 million meters per second, and the frequency is 2.4 GHz. Now we use this equation here to find the wavelength. Wavelength is equal to 300 times 10 to the 6. That is this 300 here, the speed of light, 300 times 10 to the 6. Over the frequency, which is 2.4 times 10 to the 9, okay? So we basically take the zeros off. That's how we get 10 to the 6. And 2.4 times 10 to the 9, we take the zeros off here as well, which is 9 zeros, because it's gigahertz, okay? So now the answer here is 125 times 10 to the negative 3. We subtract 6 minus 9, and we get 10 to the negative 3, which is equal to 0.125 meters. So this is the wavelength, 0.125 meters, which is equal to 12.5 centimeters. Now a dipole antenna uses half of this wavelength. So we divide this by 2. So we get 6.25 centimeters. So these two elements makes up 6.25 centimeters. So we divide that by 2. And each element would be 3.125 centimeters as you see them here. So once these elements are the correct length, 100% of your 2.4 GHz, which is a resonant frequency, should be radiated out into the airways. So next we have to calculate the bandwidth. Now this is a resonant frequency of 2.4 GHz. Now the bandwidth are the usable frequencies, both sides of this resonant frequency. Now the bandwidth depends on the diameter of these elements. The larger the diameter, the larger the bandwidth is going to be. The smaller the diameter, the smaller the bandwidth is going to be. Now if you're using 24 gauge copper wire to make the elements of this dipole antenna, you would have a smaller bandwidth than you would if you use 10 gauge copper wire like I have written here. Now because as you know, 24 gauge copper wire is actually smaller than 10 gauge. Is actually reversed, right? The smaller the number, the thicker the diameter of that wire is going to be. So in this case, we're going to be using 10 gauge, which is 0.002588 meters. Now in order to calculate the bandwidth, the first thing we have to do is to calculate the Q factor. So under here, I have the equation on how to calculate the Q factor, which is Q is equal to wavelength, this is the symbol for wavelength, over 2 times pi times A. Now pi is equal to 3.14, as I have written over here. We have 2 times 3.14 times 0.001294 meters. How I got this number here, which is the A, this is half the diameter. So you just divide this number here, 0.002588 meters by 2, and you get the A. Okay? A is called the radius. It is half of the diameter of the conductor here. Okay? And the wavelength is 0.125 meters. So once we divide 0.125 meters by this number under here, after we do our calculations, 2 times 3.14 times 0.001294, we would get 15.4, and this is our Q. So here we're going to be calculating the bandwidth, which are the frequencies both sides of the 2.4 gigahertz resonant frequency. So over here we have the equation for bandwidth, which is equal to frequency over Q. We have just calculated the Q, which is 15.4. And we know the frequency is 2.4 gigahertz, which is 2.4 times 10 to the 9. We just took the 9 zeros off, so we have 10 to the 9. So once we do the calculations here, we will get 155,844,155 hertz. And that is equal to 155.84 megahertz. So the bandwidth is 155.84 megahertz. So here we have our bandwidth of 155.84 megahertz. Now I convert that to gigahertz, which is 0.15584 gigahertz, for the simple reason that our resonant frequency is in gigahertz, so I just want to keep them all the same. So the next thing I do is to divide this 0.15584 by 2, because this total bandwidth has to be shared by both sides of this 2.4 gigahertz. So I have 0.07792 gigahertz on both sides, one being positive and the other one being negative. So under here I have F lower, which is the negative side of the 2.4 gigahertz, and F upper is on the positive side of the 2.4 gigahertz. So for F lower, I subtract 0.07792 gigahertz from the 2.4, and I get 2.32208 gigahertz. And for the upper frequency, I add the 0.07792 to the 2.4, and I get 2.47792 gigahertz. Now, this is how we get our bandwidth. But what you'll notice with this is that as these frequencies move away from the resonant frequency, you're going to have some of your frequencies being reflected back. This is called SWR, which is standing wave ratio. You're going to have a percentage of your signal being reflected back towards the transmitter. This happens because the wavelength at the extreme ends are much longer or shorter than the wavelength at 2.4 gigahertz, which is the resonant frequency. If you're on a positive side, it's going to be shorter. If you're on the negative side, it's going to be longer. And it's primarily the ones on the outer edge. The ones that are close to the 2.4 are generally okay. It's the ones on the outer edge that's going to be reflected back because they're either too long or too short. This is not a significant amount for this particular antenna. It works out to be about 4% of your signal is reflected back to the transmitter. So approximately 96% of your signal is actually radiated out into the airways and sent to the receiver. Just about 4% is reflected back. So modern transmitters are built to be able to withstand a 4% reflection. So this is how we determine the bandwidth. The dipole is a well-designed antenna. However, increasing bandwidth with thicker wire beyond 10 gauge is limited, and the thicker wire is also harder to work with. I'll be talking about how to achieve higher bandwidth in upcoming videos with antennas like the bow tie, biconical, and spiral. I've also provided links to related products within the description below that may be helpful. If this video was helpful to you and you would like to see more videos like this one, please don't forget to like and subscribe. This is Trevor from Telecom Training. Thank you for watching, and I hope to see you in the next video.